Rotational motion is also called angular motion or rotation. This is a new type of motion, and that describes a lot of motions actually happening in the real world. So we're introducing the properties and the relations between angular and linear motion, and also the equations. So from these three perspectives, we're going to look at angular motion, and the focus will be on displacement, velocity, and acceleration. So first of all, let's see. We learned the properties of the linear motion, including displacement, time, velocity, and acceleration. So here we are including the definition using algebra and also using calculus. For angular motion, the displacement is in angle. So that's in the unit of radian. Radian is the SI base unit for angle and angular displacement. What we usually use for degree is not a SI base unit. So be sure to convert that to radian if you need to do calculations. That's required almost all the time. Okay, time is in seconds. Angular velocity means the change of angle over time. So that's in radians per second. If you have learned calculus, that means the first order derivative of angular position with respect to time. And the symbol is omega. That's a Greek letter representing angular velocity or rotational velocity. And angular acceleration, the Greek letter alpha, means the change of angular velocity in unit time. Also in the calculus framework, it's the first order derivative of the angular velocity with respect to time. The SI base unit is radians per second. You can see the displacement, time, velocity, and acceleration. The definitions are similar. So we are replacing the linear displacement with angular displacement. So let's look at that in an example. So in the example of an analog clock, this hour hand is currently pointing at 3. So it's a little after 3 o'clock. And this hand will go around a full circle in 12 hours. So the angular displacement is 2 pi. 2 pi is the angle value in a full circle. Sometimes we call this a full rotation. Okay, so the time is 12 hours and we convert that to SI base units. So now the angular displacement and time are both in SI base unit. So angular velocity we calculate turn out to be this is a very small value. So the our hand looks like it's almost not rotating. It's definitely not rotating very fast. So this is an example of an angular velocity. So linear motion and angular motion are related. So the tip of that hour hand is moving in a linear fashion. So the linear distance equals to the r, which is the radius, multiplied by the angle. The linear velocity is r multiplied by omega, the angular velocity. Linear acceleration a equals to the r radius multiplied by alpha, the angular acceleration. Look at this in the example. There is a table that's rotating. It's rotating at 23 revolutions per minute. And again, revolution means a full circle. There is a coffee cup lid sitting at the edge of the table, and it's 20 centimeters from the center. So R equals to 20 centimeters converted to 0.20 meters SI base unit. So first, let's look at the angular motion. Angular displacement is 23 multiplied by 2 pi radians. That's the total angular displacement. And the time, 1 minute equals to 60 seconds. So we converted the angular displacement and time both to SI base unit. So the angular velocity is the angle divided by time in the unit of radians per second. Okay, then let's look at the relationship between the angular and the linear motion. This lid is going around with the table at a linear velocity of v. So that is in meters per second. And it's also rotating at an angular velocity of omega. That's radians per second. So v equals to omega times r, the radius. So v equals to 0.48 meters per second. That's the this is how linear velocity and angular velocity are related. Equations of motion. For linear motion, we learned previously there are two types of linear motions. One is a motion with a constant velocity. These are how the three properties related. And for angular motion, if the angular motion is at a constant angular velocity, so this is how displacement is related to angular velocity. You see the similarity between the two. And we also look at a second type of motion, that's one-dimensional linear motion with a constant acceleration, and we have these equations. And for motion with a constant acceleration in the angular framework, the equations are all similar. So the angular velocity equals to the initial angular velocity plus angular acceleration times time. The angular second equation, angular displacement delta theta equals to the initial angular velocity times time plus half angular acceleration times square. And the final angular velocity square equals to the initial angular velocity square plus 2 alpha delta theta, etc. So these are the two basic types of angular motion and linear motion. For linear motion, there's a very special case for constant acceleration. That's when the acceleration is 9.8 meters per second. That describes the particular motion of objects falling on the surface of Earth. It is a special case of the second type of motion, which is the motion with constant acceleration. For angular motion, there's no such special case. So free fall is very special. In summary, we learned angular motion, and the properties include displacement, velocity, and acceleration. And secondly, the angular motion is related to linear motion in terms of displacement, angular velocity, and angular acceleration. And finally, we learned the equations of motion. So we know how displacement, velocity, acceleration are related for one angular motion.